All right, we have, like my class now. So.
Yeah, but we know what's going on here for the most part.
Thanks. I feel like that's actually pretty good news. All right, so waiting on the screen to stop being difficult. There we go. Okay, so today we're going to talk about another type of feedback amplifier. Specifically, we're going to be dealing with feedback transconductance amplifiers. Let's just make sure, just people saying here. Okay, excuse me. So in a feedback transconductance amplifier, well, actually, let's talk about what a transconductance amplifier does to begin with. So a transconductance amplifier is an amplifier which converts a voltage signal at the input to a current signal at the output. So if we are going to try to make a feedback transconductance amplifier, we need to make sure that our feedback network is connected to the output in what way? So our output is a current signal. So we have to connect our feedback network in series there. Because our input signal is a voltage, what are we going to have to do to add another voltage to it with our feedback network? Also in series. Okay, so we're going to have a series feedback network. So in our ideal case, that is going to look something like this, where I'm just going to explicitly state again that our signal resistance is 0 ohms, our load resistance is infinitely large, and our feedback network, which I'm just going to say K, does not load our amplifier circuit. So for this particular configuration, we're going to have something that looks like this. Or these are the input terminals of my open loop amplifier network, characterized by its input impedance Ri. The voltage drop over Ri is the error signal Vi. We could also have some error current I sub I. Sorry, because we are getting a current at the output, instead of using a dependent voltage source, we'll now need to include a dependent current source, which is A1, our open loop system gain, times our error signal Vi, and our open loop output resistance R0 will be in parallel with that dependent current source. So there's the output node. So I'm just going to go ahead and draw a box around our open loop amplifier circuit. Color. Here's our output of our system. And so we are effectively just going to short this guy out, which is how we are going to connect our feedback network in series. If we were to break open these terminals and look in, that is how we would find our output resistance with feedback, which will be a lot more obvious once I connect the feedback network in just a second. Let's see. So down here will be my feedback. network. So my feedback network is going to look like a short circuit here, where we're measuring or sensing our output current I out. And then on the other side, because we are going to be adding a voltage or adding a negative voltage, going to be characterized by a dependent voltage source, where we have K, our feedback factor, times our output current is what gives us our feedback voltage VF. And so let me just highlight the feedback network. All right, so I just want to make sure that I'm not missing any little subtle parameters that we're going to have to talk about at all. I guess one obvious one would be the input resistance with feedback. And I think that is it. Okay, so our equivalent network for this guy would look something like this. Bless you. Here's O, O prime, and here is I out. So the ultimate goal of this guy is to just amplify some input voltage and convert it into some output current. All right. So we can develop our transfer characteristic equation for this system by looking at our uppermost circuit. So by inspection, hopefully, we can see that our output current I out will be simply A1 times VI because our output resistance is entirely shorted out by this winding loop around stuff. So we have I out is equal to A1 times VI, which is A1 times VS minus VF, which is in turn then A1 times VS minus K I out. And from this, we have then that I out times 1 plus KA1 is equal to A1 VS, giving us a closed loop transfer function. AF will be the ratio of I out divided by VS is A1 over 1 plus KA1. So if we connect things in this way, we do get our closed loop characteristic transfer function that we're looking for. It's kind of the crux of all this stuff. To determine how we compute our input resistance with feedback, we're going to have to look at our input loop. So just to be clear here again, I can express this right here to make it more obvious. We know that our error signal VI will be simply VS minus VF based on doing KVL around the input loop side. So we have VI is equal to VS minus VF is equal to VS minus K I out, which is VS minus K A1 VI. Therefore, VI times 1 plus K A1 is equal to VS, which means that our error signal VI is simply VS divided by our amount of feedback. The input current, II, which is the current being supplied by our signal source, okay, is simply going to be VI over RI. So we have I sub I is equal to VI over RI, which is going to be VS divided by 1 plus K A1 times RI. And from this, our input resistance with feedback, RIF, is simply VS over I sub I is 1 plus K A1 times RI. So because we have a series connection at our input, again, we observe that our input resistance, our open loop input resistance gets boosted by the application of negative feedback. All right. To determine R naught F, we have to set VS as equal to 0 and apply a test voltage between the output terminals. So what I mean by that specifically, right now, let's see, we're going to set this guy equal to 0, and we're going to replace this guy with a test voltage Vx, and the ratio between that test voltage Vx and the current leaving the test voltage, which is Ix, is our output resistance, right? So it's just the traditional means by which we measure output resistance. We zero the input, apply a test source, and then take the ratio of the test voltage to the test current. So it should be pretty easy to see here that our test current Ix is exactly equal to our output current for our amplifier, I out, because they are in series with each other and they have the same direction. Everybody okay with that? Okay, so from that, we have Ix is equal to I out is equal to, so let's look at what's going on here, okay? I'm applying Kirchhoff's current law at this node. So I know that my current I out splits between my dependent source and my open loop output resistance. So I'm just going to have A1 times VI as one of my terms. What is the voltage drop over my open loop output resistor R naught? The X, right? Because this is just a long, wild short circuit, okay? So applying Kirchhoff's current law, I can say that this is A1 VI plus Vx over R naught. So this is going to look like A1 VI in this case is simply negative VF, right? Because we have our input signal Vs shorted out. So the positive polarity terminal of VI is connected to the negative polarity terminal of VF. The negative polarity terminal of VI is connected to the positive polarity terminal of VF. So they are equal but opposite voltages. Plus that same Vx over R naught. And then finally, I can express Vf as negative K Ix. Well, I take that back. I can express negative Vf as negative Kix, right? We know that our feedback voltage Vf is simply K times I out, where I out is equal to Ix. To this, I add my term Vx over R naught, and then with the tiniest amount of algebra, I see that Ix is times 1 plus K A1 will be equal to Vx over R naught, which means that my output resistance with feedback X over Ix is R naught times 1 plus K A1. So again, now because we have a series connection at our output, we see that our output resistance is boosted as well. So this is fundamentally different than what we had going on with our feedback voltage amplifier. Okay, so just to recap things, in order to have a good feedback voltage amplifier, we need to have a very high input resistance and a very low output resistance, which is why we boost the input resistance with negative feedback and we shrink the output resistance with the negative feedback for the feedback voltage amplifier. For the feedback transconductance amplifier, it should be fairly obvious that we need a very high input resistance and a very high output resistance. So we'll see that like there's a homework problem where you're just given pictures of 4 different amplifiers, and it was kind of hard to figure out exactly what was being asked. But if you look at the input resistance and the output resistance of those circuits, it tells you what kind of amplifier it would be best suited for. So I'm just trying to make sure that I include that so that when you get to that problem, you have some idea of what the hell you're trying to do. Okay, so this is what our system looks like in an ideal state. Now let's look at it for the practical case as well, and then we'll work some example problems with transistor circuit, kind of figuring out how we should work things out. All right, so in the practical case, we have our signal voltage Vs, but we may have some finite signal resistance, which I'm going to call Rs. So this is the S terminal, this is the S prime terminal. If we look in from here, we see RIF. If we look in from here, we see RIN, which is the closed loop input resistance, excluding that signal resistance. I just want to be clear about that. Here's our open loop amplifier. Here's our output terminal. Here's our current I out. Now we can't say that our load resistance is 0, so let's include one explicitly. And I'm setting up another set of terminals here that I'm not going to name, but it's going to be fairly important. Okay, so I want to talk about these real quick before I connect my feedback system. So if we were trying to measure our output resistance with feedback, ROF. This is a terminal, a set of terminals effectively that I'm included that tells me where to break my feedback loop to measure my output resistance, okay? So it's always going to be between my load resistance and then my feedback network. This is how I'm going to break it to be able to look in and see what my output resistance with feedback is. Now I want to be clear here, I'm breaking this loop open. So I'm not looking for what's in parallel with that short circuit, because then obviously I would always just get an output resistance of 0, which is not remotely what we want for a system like this. So this is going to not necessarily make our determination of our output resistances difficult per se, but we are going to actually need to kind of pay attention to where we're breaking the loop and stuff like that. So now I will connect my feedback network. So let's just put that guy down here. And here's my current I out. This is port 2 of my feedback network. This is port 1 of my feedback network. And there we go. This is my voltage V sub F. And let me see if that error message pops up again and I have to save and restart. It's looking okay. I'm just going to go ahead and save just in case. All right, so I've got, one last thing here. If I were to remove my load resistance and look in, then obviously I would see the output resistance of the system, not including the effects of the loading resistor. All right, so all in all, our analysis for these kind of circuits is going to be very, very similar to what we had for our feedback voltage amplifiers. The only real difference is because we have a series connection for our, since the feedback network is connected in series to the output of the open loop amplifier, that is going to change fundamentally how we measure R11. So when we look in through that, the port 1 of our feedback network, everything else is going to be the exact same thing. Excuse me. So to determine R11, all right, hold on just a second. Save. Close, reopen. So to determine R11, we have our feedback network. Here's port 1. Here is port 2. And we are going to look into port 1 with port 2 open circuited now. Okay. To determine R22, we have our feedback network. Here's port 1. Here's port 2. We're going to look in to port 2 with port 1 open. And then finally, our feedback factor K. We have our feedback network. So we will apply effectively a test current that I'm just arbitrarily going to call I out. And we will measure our feedback voltage VF under the constraint that there is no current flowing into port 1. And so from this, we see that our feedback factor will be VF divided by I out, where, again, the current flowing into port 1 is equal to 0. So that's our means by which we determine our feedback factor. So now we have enough information to create our open loop circuit for to determine our gain A1. And so that is going to look something like this. Here is our open loop amplifier network. We have RS here. R11 goes here. RL goes here. R22 goes here. Here is our output current. This is also the pair of terminals where we break open to look for our output resistance. And then on the other side, we have our signal voltage Vs. This is where we look in to find our I, and our open loop gain A1 will be defined as the ratio of I out over VI, or I'm sorry, this should be VI. Okay. Once we know R11, R22, K, and A1, then we can easily determine our gain with feedback and our input resistance with feedback, output resistance with feedback, etc. So just to be super clear, from here, we can say that the gain with feedback is the open loop gain over the amount of feedback. The input resistance with feedback is simply Ri multiplied by a factor of 1 plus Ka1. And from this, our input resistance with feedback, where we are effectively extracting the source resistance out of it, is RIF minus RS. So this is just of the feedback of the network itself without including the signal resistance. Our output resistance with feedback is R naught times 1 plus Ka1. And then our output resistance, excluding the load resistor, is then simply ROF minus RL. Okay. So we're going to analyze some circuits, figure out how to determine A1 R11, R22, and all that kind of good stuff. Yes, sir. That's R sub L. Yeah. All right, you guys ready to do some examples? All right. Did I write on all 7 pages? Okay, I'm going to tuck an example in here then. I think we'll have enough room. All right, so for our first example, this would be a control circuit to limit the amount of current that's flowing through a laser diode so that we don't burn it out. So our circuit of interest is going to look like this. We have some resistance here, RD. This is going to be transistor M2. Here is our laser diode. Sorry. Here is Vn. So this is going to be transistor M1. And then here is a resistor R sub M. Okay. So just to be clear here, our feedback network, let me put a dashed line around it so we can really understand what's going on. Okay. So what I've boxed in there in pink is our feedback network. I guess I should also explain what my output signal is. My output signal here, we'll put it as I out in this particular place. So what's going on here is we have a common base amplifier effectively creating a input voltage for a source follower amplifier, and our output for our source follower stage is the current, the drain current of transistor M2. It flows through our diode, which generates light, but we know from way back in engineering 120 that if we allow too much current to flow through an LED, we burn them out pretty quick, okay? So what this feedback network does, this resistor RM is used to both sense the amount of current that's flowing through our laser diode, because we know that none of it can branch off and flow through the gate of transistor M1. And it is also responsible for converting that current I out into a voltage, which can be then fed into our mixer, which is transistor M1 as well, okay? So our feedback network here is kind of playing double duty. It is both the sense mechanism for our output current, and it is also integral to the operation of our input mixing stage, which is allowing us to actually apply the negative feedback, right? We have to have this resistor here because there's no other way that we could convert that output current into a voltage, which could then be added to our input signal. Okay. All right, so again, we're going to work all of these under the assumption that our feedback network is in some way, shape, or form loading our system. So we're not going to worry about our ideal cases too much. So in this case, our feedback network, so between our output terminal, which is the negative terminal of the diode, and our input port, which would be the gate of transistor M1, we have a short circuit. And then between that short circuit and our ground terminal, we have that measure resistor, R sub M. So this is our feedback network. R11, so to be clear, this is we look into port 1 with port 2 open circuited. What do we see? R sub M, right? Nothing wild or crazy there. For R22, we look into port 2 with port 1 open circuited. So we also see R sub M. For our feedback factor, we're just going to talk our way through this. So if I applied a current source to port 2 and measured the voltage drop over port 1 while it was open circuited, I would see that the voltage at the output, or at port 1, is simply the current times that resistor R sub M, right? And so if I divide that resistance by, if I divide the voltage seen at port 1 by the current flowing through port 2, I just get RM yet again. So for this particular feedback configuration, the measure resistance is R11, R22, and our feedback factor. So this one's pretty simple to figure out what's going on. All right, so now that we have that detailed, let's take a look at our open loop circuit. So our open loop circuit should look something like this. Here we have our resistor R sub D. Here's where our input voltage is applied. This is transistor M1. So the gate of M1 will have a resistor R11 tied between the gate and ground. Then we're looking at our output port here. So it will have the resistor R22 tied between here and ground. This short circuit here between our diode and that resistor R22 is the short that we're going to break open to determine our output resistance, our open loop output resistance explicitly. For our open loop input resistance, we're going to look here into the input terminal. Let's draw it here for the sake. Here's M2. Here is our current I out. And here is VDD. So because we're looking at this guy as an amplifier, we need to be looking at the small signal model for the diode as well. So what does the small signal model for a diode look like? Just a small resistance R sub D, I think is what we called it in 335. So I'm just going to say that this guy has some small signal resistance R sub D that we're going to have to take into account as well. Or if we wanted to, we could use the ideal diode model and just say that it looks like a short circuit. Make the math a little bit easier, but it doesn't matter which way. It's not going to complicate things that terribly much. Okay. So I can break this guy again into two stages. Effectively, if I have more than one transistor, that's going to happen a lot. I'm going to call this voltage Vx. And so I'm going to have a transfer function that is Vx over Vn times I out over Vx. Your textbook uses the open loop gain for this type of amplifier. They call it capital G sub M because it does represent a transconductance. But to me, that looks too close to the short circuit transconductance symbol. So I'm just going to stick with the generic A for open loop gain, just so that there's no potential for confusion here. Okay. So for the first stage, we see a common gate amplifier with some resistance R11 tied to the gate. What does that resistance R11 do to a common gate amplifier? Absolutely nothing. So our transfer function for our first stage should literally just be the input-output relationship for a common gate amplifier, which is, Ronnie, you nailed it on Monday. Can you tell me what it is again? Okay, so that is not correct. That's not going to be the gain. All right, somebody else. What's the gain of a common gate stage? GMRD. So Vx over Vn is equal to GM1 times RD. Now our second stage is a source follower stage effectively, but we can't simply use a source follower input output relationship because that is a voltage amplifier and we are looking specifically for the output current. So I can say pretty concisely that our output current, the small signal current of our amplifier, is going to be GM2 times VGS2, because that's what a transistor does. Converts the gate source voltage into an output current by means of the transconductance. Okay? So this is our starting point for figuring out what our output current is, and now we need to develop some relationships to relate probably VGS2 to the quantity Vx. Okay. So I would say that this is GM2 times Vx, which is the voltage at the gate terminal with respect to ground, right? Minus, now we need to figure out what the voltage at the source terminal is with respect to ground. Anybody have any thoughts? Yeah, so I out times RD in series with R22. Sorry, lowercase r, lowercase d for the dynamic resistance of the diode. That would have gotten awkward quickly. And so I can see from this that I'm going to have I out times 1 plus GM2 RD plus R22 is equal to GM2 Vx, giving me a transfer function I out over Vx that is GM2 divided by 1 plus GM2 RD plus R22. Everybody okay with my algebra there? So from this, my overall open loop gain, A1, is just the product of my two transfer functions. So that's going to be GM1, GM2, capital RD, divided by 1 plus GM2 RD plus R22. Over here, what is my open loop input resistance? No. Oh, wait, actually, I might be wrong on this one. Crap, I was blanket saying it's infinity, but no, you're correct. It should be 1 over GM, right? Because we were looking into the source terminal. Yeah, so I had a total brain fart when I was kind of coming up with my notes. Thank you. So yeah, 1 over GM1, which would typically be pretty small. So it makes sense that we need to boost it by some large amount, okay? For our open loop output resistance, I would argue that it's kind of hard to see directly what's going on here, okay? So I'm going to draw a small signal model for this. All right. So I have my gate terminal, and because I'm looking for output resistance, I need to short my input, which would be node X, to ground. Here I'm going to have VGS2. So this is my gate terminal of transistor 2. This is my source terminal of transistor 2. So up here would be my drain terminal of transistor 2. So this is going to be GM2, VGS2. My drain is connected to AC ground. So this is D2. Then I have my diode resistance RD. Here's my resistance R22, right? And I'm looking in through that open circuit network to figure out what's going on. So one thing that I want to be clear here, we can tie those two drains together when those two grounds together when I draw my equivalent circuit to figure out what's going on here. So I'm going to apply a test voltage, Vx, and measure this current, Ix. So let me ask you guys just a quick question here. Will it change any of my relationships whatsoever if I combine RD and R22 into one series resistance? Is it going to change what VGS2 is in any way, shape, or form? No, right? It's not going to change the current flowing through the network or anything like that either. So to me, what this looks like is the following network. Here I have Vx, this is my current, Ix, then I have this guy right here, which is GM2, VGS2. This node right here is my ground, and so I can see that I would have R22 plus RD here, okay? Now, one thing that I want to point out, the positive polarity terminal of VGS2 is at my ground location, and the negative polarity terminal of VGS2 is connected at the positive polarity terminal of my voltage Vx. So, oops, that was a little too much of an erasure. I could write it like this, negative VGS2 positive. And if I wrote a KVL equation around this loop, I would have negative Vx minus VGS2 plus Ix times R22 plus RD is equal to 0. What is the relationship between VGS2 and GM, or excuse me, Ix and my dependent current source? Same but opposite direction, right? So I can say that Ix is equal to negative GM2 VGS2, which implies that VGS2 is just negative Ix over GM2, right? If I substitute this relationship into my KVL equation, I get Vx is equal to negative, so it's going to be positive Ix over GM2 plus Ix times R22 plus R lowercase rd. I apologize. And from this, my open loop output resistance is 1 over GM2 in series with RD in series with R22. So if I were measuring an output voltage and taking the output resistance from this point, I wouldn't need to break open that node. So I would see R22 in parallel with lowercase rd in series with 1 over GM. But because I'm taking an output current here, I have to break open that node and look in through those terminals. Otherwise, I would see just the short circuit, okay? So I want to be clear about this and how we calculated it, because we are so used to just measuring a voltage at the output and then saying, oh, so it's going to be whatever I see up in parallel with whatever I see down, because we're not breaking open that point in the circuit, okay? So that's why this is fundamentally different. So effectively, we have whatever we see up in series with whatever we see down, not in parallel. So I just wanted to be real clear about that, because that's a real easy place to make a mistake, because you're just so fundamentally used to doing it the other way. All right, we only have 20 minutes left, so I'm going to skip over one of the example problems that I had worked out, and we'll go to one that's the most complicated one, which really, in the grand scheme of things, isn't all that complicated. All right, so this circuit is what's called a feedback triple. And so it's got 3 gain stages built in. That is VDD. Here is Vin. This is going to be transistor M1. This is going to be resistance RD1. This is transistor M2. This is transistor, or excuse me, this is transistor M3, that's resistor RD3. I'm also going to have a resistor here, RD2. Here is where my output current is. Here's resistor R2, and that certainly doesn't look like a 2 at all. I apologize. This guy is going to be R1. And this guy is going to be R3. So again, we have a feedback network of resistances, which is both sensing the output current and then also converting that output current to a voltage so that it can be applied to our mixer. Okay. So this is where we would see RIF looking in through this short circuit is where we would see the resistance ROF. So our feedback network looks like this. Here's port 1. This is resistor R1. Here's resistor R2. Here's resistor R3. And here is port 2. All right. So R11, again, is determined by looking into port 1 with port 2 open circuited. So what would we see? That is correct. R1 in parallel with the series combination of R2 and R3, and therefore R22, which we look into port 2 with port 1 open, is then just going to be R3 in parallel with a series combination of R1 and R2. To determine our feedback factor K, this is going to be a little harder than just doing it effectively by inspection. So what I'm going to say here is that we have some known current I out flowing through that node, and we are trying to determine this voltage right here, VF, right? So I could say that I'm going to call this current right here I1. I could say that my current I1 is going to be I out multiplied by R3 over, R1 plus R2 plus R3. That's just current division where instead of using the reciprocal formula, I'm using the one where I'm saying the current through this branch is the resistance of the opposite divided by the total resistance C. You would get the exact same result if you use the 1 over R2 plus R1 divided by 1 over R2 plus R1 plus 1 over R3. Making it smaller so it'll be a little bit easier to do algebra on in a moment. Obviously, then we could say that I out is I1 times R1 plus R2 plus R3 divided by R3. We know that our voltage VF is just I1 times R1. And so our feedback factor K, by definition, will be VF over I out. So that's going to be, this thing will write, I1 R1 divided by R1 plus R2 plus R3, and I'm dividing my denominator by R3, which is the same as multiplying my numerator by R3. Crap. And I should have a factor of I1 here as well. These guys cancel out, and I'm left with R1, R3 over the sum of R1 plus R2 plus R3. Everybody follow my logic for determining the feedback factor here. Choosing current division and Ohm's law and a tiny amount of algebra. All right, so we can now construct our open loop circuit. So that's going to look something like this. Here is RD1. Here is transistor M1, to which I apply my input signal. And R11, again, is always applied at the input port node there. Then over here, here is RD2. This is transistor M2. This is resistor R22. Here is my output current, I out. Here is VDD. And here is RD3. So this is just 3 common source stages cascaded into each other. 2 of them happen to have degeneration, okay? So obviously then, if I call this guy X and this guy Y, my overall open loop voltage gain is going to be Vx over Vn times Vy over Vx times I out over Vy. So we're going to have to pay attention to that third stage again, because we're converting that voltage into a current, so we can't simply use the voltage transfer relationship for a degenerated common source amplifier. So our first stage, we have Vx over Vn. Again, it's just a degenerated common emitter amplifier, common source amplifier, because these are totally MOSFETs. So it's going to be GM1 times RD1 divided by 1 plus GM1 R11. Vy over Vx is a common source amplifier with no degeneration. So it'll just be negative GM2 times RD2. For our last stage, we know that I out is going to be GM3 times VGS3, where VGS3 is Vy minus I out times R22. Everybody okay with that? Hopefully nothing too wild or weird there. And from this then, we can see that we have a transfer function of I out over Vy will be GM3 divided by 1 plus GM3, R22. Combine these three gain stages together, giving us an open loop gain of GM1, GM2, GM3, RD1 times RD2. Sorry, I missed having RD2 in my notes. Yeah, so the negative signs cancel each other out. I have all three transconductances, then RD1 times RD2. And then down here, I'm going to have 1 plus GM1 R11 times 1 plus GM3 R22. So fairly straightforward, even though, even though this guy looked fairly complicated, the analysis is fairly straightforward. My input resistance, open loop input resistance this time is actually going to be infinity because I am looking at the gate terminal, not the source terminal. I apologize for my mistake earlier. Based on what we learned with the previous problem, so just to be clear here, we're looking in through here to find RI, and we're breaking open this guy right here and looking in to find R0. So what should we expect based on our previous example? No work whatsoever. What we see up in series with what we see down. So what do we see up? 1 over GM3. What do we see down? R22. So we have 1 over GM3 plus R22. And we've gotten all the different parameters that we would need to understand how this guy works in a closed loop circuit. So are you getting a little bit more comfortable with this practice of generating your open loop circuit and then calculating the gain and all that kind of good stuff? All right. Like the examples that I'm doing later on in the class are, I would argue, much harder than what you would see on your test. And I don't feel that these are too wildly difficult. Okay. So if you disagree and you want me to do more problems or something, I'll try to figure something out, but we only got 2 days left of class and 2 amplifiers left to cover. So we'll figure something out. But anyway, so that's enough out of me for today. So unless you have any questions, I will see you guys on Monday, where we will cover either trans impedance amplifiers or current amplifiers. Don't know, haven't started my notes yet.